Ever wondered how to effectively determine macromaterial fractions in a complex geometry? The recursive bisection method might just be the solution. This method, as the name suggests, involves a process of continuously bisecting or dividing a given space into two equal parts. This process is repeated or recursed until a desired level of precision is achieved. At the heart of the recursive bisection method is a principle of mathematical optimization, a way to efficiently solve problems that involve complex geometrical spaces. By breaking down these spaces into smaller, manageable chunks, we can more accurately calculate the macromaterial fractions. This method is particularly useful in the field of nuclear physics, where it is often used to model and analyze the behavior of nuclear materials within a reactor. So, let's delve deeper into this intriguing method. Understanding this method can greatly assist in complex computations, as we'll discover. The first step of the recursive bisection method involves point testing. But what exactly does that mean? Well, let's dive right into it. Consider a voxel, the three-dimensional counterpart to the pixel. It's essentially a box that contains different materials. Now, in point testing, we're looking at the centers and the corners of these voxels. We're comparing the materials found in these two sets of points to see if they match. Imagine a voxel that's filled with two materials, say copper and iron. The center might hold a chunk of copper, while the corners could contain iron. In this case, we say that the voxel center's material differs from that of the voxel corners. But what if all points, both the center and the corners, are filled with the same material, like copper? Then we'd say that the voxel is homogeneous, as the material is the same throughout. Now you might be thinking, why does this matter? Well, this is where the beauty of the recursive bisection method comes into play. By comparing the materials at the voxel centers with those at the corners, we can determine whether a voxel is homogeneous or heterogeneous. If a voxel is heterogeneous, meaning its center's material differs from its corners, we divide the voxel into 8 smaller voxels. We then repeat the point testing for each of these new voxels. This process continues recursively, hence the name recursive bisection method, until we reach a level of homogeneity that satisfies our criteria. On the other hand, if a voxel is homogeneous, we leave it as it is. There's no need for further subdivision because the material is consistent throughout the voxel. The point testing phase, therefore, gives us a way to break down complex structures into simpler, more manageable pieces. It's a crucial step in the recursive bisection method, allowing us to accurately represent the distribution of materials within a voxel. And that's the gist of point testing. It's an integral part of the process, setting the stage for the subsequent steps in the recursive bisection method. Point testing is an essential step in the recursive bisection method, setting the stage for the next steps. Now that we understand the first step, how does this apply in a real-world scenario? This is the question that often pops up when we're grappling with complex algorithms and methods. Let's delve into an example that speaks to this query. Imagine we're dealing with a cast geometry filled with a variety of materials. Now, this isn't just a simple mix. We're talking different densities, different compositions, and different properties. It's a veritable melting pot of complexity. This is where the recursive bisection method truly shines. By utilizing this method, we can significantly improve our Denovo models. Now, what does that mean exactly? Well, Denovo in this context is a high-level computational tool used for neutron transport calculations. It's a workhorse in nuclear science and engineering studies. Through the recursive bisection method, we can enhance the accuracy of our Denovo models. It allows us to divide the volume of the cask into subcells. Each subcell then represents a fraction of the total material within the cask. This process aids in generating a precise representation of the material distribution within our cask geometry. Now let's talk about some parameters that play a crucial role in this method. subcells and tolerance. The subcells parameter dictates the maximum number of subcells that can be created during the bisection process. It's our control knob for the granularity of the model. Then we have tolerance. It's a measure of how close our approximation needs to be to the actual material distribution. It's our gauge for the accuracy of the model. Too high, and we might miss some crucial details. Too low, and we might end up with an overly complex model that's difficult to handle computationally. So we see the recursive bisection method is not just an abstract concept, it's a practical tool with real-world applications. It's a bridge that connects the world of theoretical algorithms to tangible computational modeling tasks. This example illustrates how the recursive bisection method can enhance complex modeling tasks. It's not just about understanding the method, but also about knowing when and how to use it effectively. A critical part of the recursive bisection method involves the starting sources block. But what is it, you might ask? Well, let's dive into the nuts and bolts of this fascinating component. In the world of Denovo, a computational tool used for nuclear radiation transport calculations, the starting sources block plays a pivotal role. It's the foundational stone from where the recursive bisection method begins its journey. The starting sources block is like the starting line of a race, marking the point from which all computations and simulations kick off. Now, let's talk about the default settings. By default, the starting sources block is set to initialize a uniform source distribution. This means that each and every voxel or three-dimensional pixel of the material under scrutiny starts with the same amount of source material. It's like giving everyone in a race the same running start. However, the beauty of Denovo lies in its flexibility. It allows users to customize these settings. So, if you're feeling adventurous, you can tweak the starting sources block to initialize a non-uniform source distribution. It's akin to giving some runners a head start in the race based on certain conditions or factors. Now this brings us to an interesting topic: potential improvements. One such improvement could be to initialize the starting sources based on previous outputs. This means instead of starting each race from scratch, you can use the results of the previous race to decide who gets a head start in the next one. It's like learning from the past to better predict and prepare for the future. Another potential improvement could be the implementation of an adaptive initialization approach. This approach could adjust the starting sources based on the material properties or the computational requirements of the task at hand. It's like tailoring the race conditions based on the abilities and strengths of the runners. Understanding the starting sources block provides a deeper insight into the recursive bisection method. It opens up a world of possibilities for optimizations and improvements, making the journey to the finish line, or in this case the solution to the problem, faster and more efficient. The sequence output from a simulation can tell us a lot, but what exactly should we be looking for? Well, the sequence output from Denovo simulations is packed with valuable information that can guide us in our research. Key among these are the warnings and errors that may arise during the simulation process. These are not just indicators of problems. They can be insightful pointers to areas that need adjustment or optimization. But how can we interpret this output data effectively? It's not just about identifying issues. It's about understanding what these issues mean in the context of our broader research goals. For instance, an unexpected error might signal a need to adjust the parameters of our recursive bisection method. So keep in mind, interpreting the sequence output isn't a mere troubleshooting task. It's a crucial step in fine-tuning our approach and refining our results. Properly interpreting sequence output is key for successful implementation of the recursive bisection method. We've covered a lot of ground today. Let's go over the key points. We started with an introduction to the recursive bisection method, a technique used to determine macromaterial fractions. We then delved into the point testing phase, where we observed how this method compares materials at voxel centers with those at corners. An example of a cask geometry with various materials was presented, illustrating how the Denovo model improves with the recursive bisection method. We discussed parameters like subcells and tolerance, and moved on to the starting sources block in Denovo, emphasizing the importance of user customization options. We ended with interpreting the sequence output from Denovo simulations, noting the significance of examining warnings and errors. Sarah's insights prompted a lively discussion on interpreting output data effectively. The practical application of the recursive bisection method was made clear through these discussions. With these key points in mind, the recursive bisection method becomes a powerful tool for research and complex computations.